Math 1343, Week 11, Video 1, Post-ANOVA Analysis Introduction. At this point, if you've been following everything we've been doing, the last series of videos and the last homework and quiz was over analysis of variance, or ANOVA, if you will. The goal of which was to test multiple population means to see if they were all equal. And so at the end of the test, you drew one of two conclusions. Either all of the population means are equal, or there was sufficient evidence to conclude at least two of them weren't equal. Before we get into what we're going to do post-ANOVA, in other words, after an ANOVA test has been performed, let's quickly review the information that we're given and the conclusions that we can draw. I've got a scenario set up here where and bank. I know why the word "and" is there, but I didn't catch that in the final edit. A bank wondered if their ATMs were used equally during a given year. A random sample of 3 ATMs were selected. Sample was selected. I'm nitpicky on my grammar. A random sample of 3 ATMs was selected, and a random sample of 8 days was selected. The bank recorded the usage of each ATM over these 8 days. Below is the data, summary statistics, and ANOVA table at a 5% significance level. Now, I promise you, I looked over this for typos, and it doesn't matter. There's always going to be more. All right, so let's see what we got. We've got 3 ATMs, which, and I'm going to try a new feature here in. Oh, there we go. Ooh, that's pretty. Sorry, I'm playing with more. Okay, that's not bad, but let's go back to that. That was cool. Can I get rid of that thing? Hold on, folks. I may have accidentally done something I didn't want to do. Go away, arrow. That's not me. We'll just throw the arrow up there and pretend it's not. All right, so over here, we have the samples gathered from each ATM. For the first ATM, these 8 numbers, or the days, the number of times the ATM was used each of those 8 days. Right here, we have the same thing for the second ATM, and right here we have the same thing for the third ATM. In this table, we have the sample sizes, which were all 8. The mean number of times the ATM was used over the 8 days period, 30.75, 34, and 49.25. And the standard deviation of each sample, 9.25, 14.63, and 10.79. Now, I've spared all the details about calculating the SS's and then following through with the ANOVA table, but we do have the ANOVA table down here, complete with the degrees of freedom, the SS's, the MS's, and just a reminder, each MS, like the 70.85, that thing's bothering me. Let's go to highlight. I still don't know how to get rid of that arrow up there, so I'm not going to worry about it. But anyway, each MS was just the SS divided by the degrees of freedom. That one's pretty easy to see. Half of 1561 is 780.5, at least with the calculator, so you can see. And then the same thing with the MS here, where we took 2913 and divided it by 22. And then to get the F statistic, which is the test statistic on our ANOVA test, we simply divide the MS's, the top one divided by the bottom one. Now this table also includes a p-value, but I do want to remind you that the F here is the test statistics. So if we were doing the critical value approach, we would compare it to the critical value, which is not listed here. And if we landed in a rejection region, we would reject the null hypothesis, which is all the means are equal. But if we're doing the p-value approach, which would be a little bit easier because at the p-value, then we would simply compare it to the significance level and make the correct decision. Since this p-value is less than 5%, we would reject the null hypothesis. In fact, let's go ahead and say how this ANOVA would end because of the p-value compared to the significance level. Since the p-value is less than the significance level, I was worried about misspelling significance. We reject the null hypothesis which is all means are equal. Thus, we have sufficient evidence that at least two of the means are different. So that would be a good way to close that ANOVA test. But it kind of leaves things up in the air, because when you reject the null hypothesis in an ANOVA test, and for those of you who are really statistically savvy who are watching this, I know I'm not saying one-way ANOVA test, but in the class I'm teaching, that's the only ANOVA we know so far. But in this ANOVA test, we concluded that at least two of the means are different. But there are some questions, or at least one big question, that should jump out at you. Okay, you say at least two of the means are different, but you didn't tell me which ones. Now, we can speculate and say, well, let's look at the means, and let's go highlight the means so that they stand out. If we look at the means, right here, that's supposed to be highlighted, but I think that box will work. If we said which ones are different, well, on the surface, they all look different. But remember, these are samples, and samples don't always, they attempt to mirror the population, but they're not always exactly how the population plays out, which is the whole reason statistics exist, or at least inferential statistics. So we can't really just look at those three sample means and say they're clearly different, therefore the population means are different. But our ANOVA test suggests that we have strong enough evidence that at least two of the population means actually are different. So, which two do you think it would be? The natural one to go to is the smallest compared to the largest, because those two are most different. And so if our analysis of variance says at least two of them are different, those are the most likely candidates. But what about the 34 and the 49.25? Are those different enough? Remember, ANOVA says at least two of them are different. It doesn't say which one. Well, what about the 30.75 and 34? Are those different enough to say that their population means might be different? So the conclusion of the ANOVA leaves some unanswered questions, especially if the conclusion is at least two of the means are different. It doesn't say which ones. So in this series of videos, what we're going to do is follow up with that and look at three different ways to look at the means after ANOVA. In fact, one of the three different ways doesn't even compare two of them, but it just estimates one of them using the confidence interval. All right, so let's go to the next video and begin our actual post-ANOVA analysis.